Chapter 15, Common Data Analysis Mistakes. In the last chapter, I walked you through the major types of graphs and charts that we use to look at data and the pros and cons of those. In this chapter, I'm going to walk you through the common mistakes that people make when they're doing data analysis. There is an almost infinite number of mistakes that can be made. However, I would like to walk you through 9 of the most common mistakes that I see data analysts and data scientists make, because I want you to be able to avoid them. The 9 most common data analysis mistakes are vague or incomplete objectives of the analysis, inaccurate or incomplete data, misunderstood data, bias, and goodness, there are many kinds of bias we deal with, data dredging, unequal comparison, correlation may not equal causality, relying on summary metrics, or using the wrong visualization. Here's the big learning point. This is far from an exhaustive list. There are almost infinite number of mistakes that can be made, but these are the most common ones. If we understand these 9 and really work actively to remove them, we're probably going to have a pretty good analysis on our hands. Vague or incomplete objectives for an analysis is so common. And when you have this situation, it can result in poorly collected data, vague outcomes, and ineffective, if not really, a straight out misleading analysis. If you're a data scientist or really a business analyst, better begin your analysis with a clear hypothesis to test. Some of the key ways we can avoid vague or incomplete objectives is, hey, 1, develop a clear hypothesis that has a meaningful impact. So let me give you an example of one that does not. Suppose you're a financial institution and you're going to do some A and B testing. So you're going to have a control group, then a test group. And you're going to do it on consumer hair color and its impact on customer retention. Is this really going to provide a positive impact to your bank or financial institution? I'm guessing it doesn't. You may say I'm biased on that, and that would be a very entertaining and, and interesting response, but probably that isn't going to make a whole lot of difference in our customer retention rate. So make sure you have a good hypothesis that's clear and that can have a meaningful impact. Also, don't assume results too quickly in the process. Many times we think we're going to pull a set of data, we're going to spit out a report, we're done. No. Good scientific method is iterative, so don't be afraid to use that iterative process. Also, another good way to overcome the vague or incomplete objectives, only test one variable at a time. As soon as you start adding multiple variables, they can skew results. So that's another technique to try to start with maybe one variable at a time, understand that variable before adding a second or a third. All right, it's time to explain how the sausage is made. Number 1, data is always imperfect or incomplete. Almost always, I should say. The question is really, what degree is it imperfect or incomplete? Because one of the things that's important is we cannot let perfection become paralysis. Sometimes good enough is the limit we can reach. However, we should strive always for good, complete, accurate data to the best we can get it. Understanding that perfection is pretty difficult to reach. There's a great line that I enjoyed reading. We every day look at numbers, indicators, percentages, and electoral maps, thinking they are the final answers to our questions, but they really are. Rarely are. No data is perfect nor objective. And if we recognize this, we can start seeing data as the beginning of the conversation and not the end. Great quote. I think Georgia hit the nail on the head with this one. So while we always are striving for complete and accurate data, understand that we can't let the striving for perfection cause paralysis. Misunderstanding data is another classic mistake that happens in data analysis. Most companies and organizations have not defined their critical data elements at an enterprise level. Therefore, they don't have enterprise data definitions, valid values, correct formats. In fact, many companies don't have effective enterprise metadata management, which is essential for all data literate organizations. Again, what does metadata management provide? It provides the who, what, when, where, how, and why of our data, and it's seminally important for any organization. Even those organizations that do have data definitions, some of them have circular definitions. The classic example is, let's suppose we have a critical data element of customer number, and they define a customer number as the number of the customer. This is an awful definition. Why? It's circular, meaning the definition itself tells you nothing in addition to what the name of the business term tells you. Because customer number is the exact same information as the number of the customer. Terrible definition. We see these all the time in the real world. Remember, data, when we talk about understanding data, it does have a human element to it, as humans define and manage the data. So it's going to have little tweaks in there that can sometimes cause issues. Trust in our data and our analysis is affected when bias seeps into the data. Bias can come in many forms. I'm going to share with you 18 types of bias that we commonly see in the field. And here's the big thing. When you're building an analysis, when you are looking at data, ask yourself, which of these types of biases do you think has come into play? Or if you're the one building the analysis, what is your plan to remove each one of them? Maybe it's not applicable based on the data that you're doing, the analysis you're doing, but you should at least look at each one of these to say, hey, how are we removing this kind of bias? Okay, ready to learn about the 18 types? Well, I'm ready to teach them to you. Anchoring. This is a cognitive bias that causes an individual to subconsciously use an initial piece of information as a fixed reference point or an anchor in the process of decision making. So for example, let's suppose you build a multi-stage analysis where you're going to have a business analyst will look at one piece of data and have that drive a decision-making process once they look at another one. You want to be very careful to not allow that initial piece of information to create this anchor that just forces, even if it's subconsciously, a person down a particular path rather than letting the data drive the decision. Okay, next type of bias we see, a bias that appeals to fear. This is when there's a persuasive message or analysis or data point that the whole purpose of it is to attempt to arouse fear by emphasizing the potential danger that will befall an organization or a group if they do not adopt the message's recommendations. Okay, next kind of bias, backfire effect. This is a cognitive bias that causes people to have increased conviction in their belief, even when faced with opposing evidence. So even though you really believe in something, you do it even though the evidence is pointing you to a different direction. Bandwagon effect. Gosh, this is quite the phenomenon. This is a phenomenon in which people do something primarily because they see someone else doing it. They see other people doing it. You may have the president of a company say, oh, our significant differentiator is the quality of our product. Then everybody parrots that. But is it really your differentiator? What data do we have that proves it is or disproves it? Common mistake, this bandwagon effect. And it's a typical type of bias that we see. Confirmation bias is the tendency to look for information that supports rather than rejects one's preconceptions, typically by interpreting evidence to confirm existing beliefs while we're rejecting or ignoring any conflicting data. Confirmation bias happens all the time in data analysis. You'll have somebody come in with a biased hypothesis, and they're going to look for data that absolutely confirms their hypothesis, their alternative hypothesis, rather than picking the right data and letting it take them where it might. Discrimination. This is the unjust treatment of people or even groups of people based on the groups or classes they belong to. This is something that in data analysis we don't see all the time, but in certain organizations, especially federal organizations where they're looking at individuals maybe a little bit differently than corporations do, discrimination can come up. Guilty by association. This is the attempt to discredit an idea based upon disfavored people or groups associated with it. You know, that's a lousy idea because this group likes it or this group of people likes it. That is poor, that is bias, and it's something we want to remove. Next, hasty generalizations. This is a fallacy in which a conclusion that we reach is not logically justified or sufficient or unbiased. We just jump to that generalized conclusion quickly when the data hasn't taken us there. Next, herd mentality. Oh boy, this is similar to some of the other biases, but it's a phenomenon where people rationalize a course of action based on the fact that other people are doing the same action. We see this a lot, not only in data analysis, but just in life, where something becomes popular and people just blindly follow it. Herd mentality, not something that we want to partake in. It's a bias and one we really want to try to minimize as much as we can. Hindsight bias refers to a psychological phenomenon in which people convince themselves that they correctly predicted an event before it occurred. I knew so-and-so would win the Super Bowl. That's really easy to say after it happened. So hindsight, I gave kind of a simplistic example, but we certainly see this in data analysis as well, is where people try to convince themselves that they correctly predicted something before it occurred, but they're doing it after the fact. Next, negativity bias. This is where we have an emotional response to negative events which feel amplified as compared to similar positive events. So we're putting a much greater emphasis on the negative than we should as compared to similar positive events. Prejudice. This is an assumption or an opinion about someone or something simply based on the person or thing's membership to a particular group. Racism. This is the belief that a person or group's race is a fundamental determinant of human traits and capacities. And these are all types of bias that we want to remove anytime we're working with data. Sampling bias occurs when conclusions are drawn from a set of data that isn't representative of the population that we are analyzing. Classic problem that we see. Next, self-serving bias. This is the tendency people have to seek out information and use it in ways that advance their self-interest rather than letting the data drive the decision. Classic problem. Sexism. This is judging people by their gender when gender really doesn't matter. Now, if we are doing an analysis where we are actually looking at the buying habits of females as compared to males or vice versa, that's different. But this is putting a judgment on someone based on gender when it really doesn't matter. It's not pertinent to the analysis. Slippery slope fallacy. This occurs when someone makes a claim about a series of events that would lead to one major event, usually a bad event. So this is when, hey, we see a series of things happening, some points in our data, and we're using this to say, hey, some really major event is about to take place. Typically, you see it as a bad event, but not always. Sometimes it's the other way around. The last but not the least bias that we will see sometimes in analysis are stereotypes. And a stereotype is to believe unfairly that all people or things with a particular characteristic are the same. And the key thing is unfairly. So if the characteristic is height, and we are saying, hey, everybody who's 6 feet 5 inches tall is really tall, that's not unfair. Probably true. I think it would be for most people. Anyway, so that wouldn't be unfair. However, if we were to say, oh, anybody with dark hair is tall, well, nope, that's not quite true. So anyway, it is an unfair belief that all people or things with a particular characteristic are all the same. Typically, that's not the case. Let me wrap up this section on bias. Bias always happens. There's always some level of it within an analysis. Here's what we need to do. Number one, we need to acknowledge it, that it happens, whether it's in reports, presentations, interpretations, whatever it might be. Great data analysis actually has a documented plan with established research mechanisms to reduce bias to the extent that it's possible. So have a plan for that. If you're a data scientist or a business analyst, to reduce and remove as much bias as you reasonably can. The next common data analysis mistake I want to speak about is data dredging. You may hear the term data fishing, data snooping, data butchery, p-hacking. It's all the same stuff. And this is the misuse of data analysis to find patterns in data that can be presented as statistically significant, thus dramatically increasing and understating the risk of false positives. Data dredging often happens when a data scientist has successfully tested a hypothesis against a particular set of data. And then they take that exact same set of data and make the mistake of testing multiple new hypotheses against it without doing all the upfront work that they typically need or should be doing. Learning point: practice care when using data for any activity, especially analytics. We want to avoid presenting false patterns or using data to fish for preconceived hypotheses. Comparing multiple data sets is a common technique for combating bias. However, this technique can suffer from a bias known as I shouldn't say a bias, a mistake known as unequal comparison. This occurs when two data sets of unequal weight are compared against each other. So let me give an example. An analyst could take two reports that look at product sales by month over month. However, if they fail to acknowledge seasonality, for example, the Christmas buying season or the weekend effect, more shopping happens on the weekend during the weekday, then the comparison is most likely going to be unequal. Anytime you're comparing multiple data sets, make sure the data sets carry equal weight before drawing a conclusion. You don't want to have one data set that has Saturday, Sunday data and compare it against Tuesday, Wednesday to try to combat bias. Those are two different things. Correlation does not always equal causation. A classic goal of many analyses is to find correlation, right? We want to find correlation because we think that'll drive us to causation, but this is not always the case. I'll give you an example. Let's suppose 100% of it. So let's suppose we have a statistic that shows out of adults who have died over the past year, 100% of them have eaten an apple at some point in their life. We have a perfect correlation coefficient. It equals 1, the highest we can have. Therefore, apples cause death. Wrong, they don't. They're actually pretty good for you. Anyway, but a great example of correlation does not always equal causation. Correlation tells us only how strongly a pair of quantitative variables are linearly related. It does not explain the how or the why. We need other analyses to do that. So give an example. Let's suppose sales from, we have a hypothesis that sales of air conditioners are related or correlate with sales of some sunscreen. The question is, are people buying air conditioners because they bought sunscreen or vice versa? No, no. The cause of both purchases is clearly something else. In this case, it's probably hot weather. Learning point. Establishing that one thing causes another takes a detailed, methodical, and unbiased analysis. Relying on summary metrics is another classic mistake we see. And too often people who are not as data literate decide on a conclusion based on these kind of summary metrics. Data sets with similar summary metrics can contain huge variances. Let me give you an example. Let's suppose product sales are surging. However, there's a marketplace event like the Super Bowl, a presidential election, holiday significant news events, etc., that is artificially inflating the purchases for a product category. In reality, sales could be down across the board. However, this one product boosted by the marketplace event is covering up the issue. I remember working with a company at one point where their sales were increasing. They were increasing 5 to 7% a year. However, so you'd think, hey, everything's going great. However, they were in a rising market. Their market was growing 20 to 30% each year. So in reality, their sales were actually lagging where they should be. Learning point. Always carefully study the raw atomic data. Remember, atomic data is our lowest level of granularity. Do not just take the summary metrics at face value before proceeding to a conclusion. The last data analysis mistake I want to speak about is using the wrong visualization. Not all visualizations are meant for all analyses because each type of visualization has its strengths and its weaknesses. A pie chart performs a very different analysis than a Venn diagram or a choropleth map. Choropleth maps, wonderful for where data is geographically dispersed, where we're looking at phenomenon across regions. Venn diagram, terrific for showing overlap between two groups. Pie charts, wonderful for showing pieces of a whole. Each type of visualization has its strengths and weaknesses. Make sure to select the right visualization for the right analysis. Time to summarize this chapter. I walked you through the 9 most common data analysis mistakes. Things like vague or incomplete objectives, data that's incomplete or inaccurate, data that is misunderstood, the 18 types of biases. It's critical. When you're building an analysis, look at these 18 types. Make sure you have a plan to combat them. Because guess what? Bias always exists to one degree or another. It's a question of, do we admit it's there? Data dredging, unequal comparison, correlation may not equal causation, relying on summary metrics and using the wrong visualization are all classic mistakes that I want you to avoid.